here, I guess. And there's obviously homework problems like this, okay? The idea is this should become like secondary to you. I guess if you do enough of these exercises, it just becomes second nature. Here's a third order equation. Third derivative of y with respect to x, right? Minus 6 times the second derivative of y with respect to x, plus 11 dy dx. Third minus 6 plus 11 minus 6y is equal to 0. Okay, again, it's always good to classify this in your mind. What is that? That's a linear differential equation of order 3, because the highest derivative is the third derivative, and has constant coefficients, and it's homogeneous, right? There's no function of x on the right-hand side. And again, as I promised you, before the course is over, you'll be able to solve that on your own. Okay, but at this stage of the game, we don't have the machinery, so I'm going to have to give you at this point what the 3 solutions are. Okay? And again, third order equation, first thing that should come into your mind, I gotta have 3 linearly independent solutions. And once I have that, I got the general solution. It comes out that the solutions are the following. One homogeneous solution is e to the x, okay? The second homogeneous solution, y2 of x, is e to the 2x. And the third solution, y sub 3 of x, is e to the x, e to 2x, and e to 3x. Okay. I will do this, again, you're not responsible for this, but those who do have linear algebra, let's talk about this without linear algebra first. Okay? Imagine, you know how to graph e to the x, e to the 2x, e to 3x, and kind of, just by looking at it, again, heuristically, you're pretty sure that these functions are linearly independent, right? Because if they were dependent, you'd have to be able to write, for example, e to 3x as a linear combination of e to the x and e to 2x. But again, you have to be careful. Again, just because it escapes your ability doesn't mean it can't happen, okay? So I want to just be careful over here. That's why you need the Wronskian really to do it rigorously, okay? But again, just on a heuristic, basis, one would venture that those 3 functions are linearly independent, okay? And again, I'll just put the result here. If you had linear algebra, you should verify it. It comes out actually that the Wronskian of these guys, e to the x, e to the 2x, and e to the 3x, those will come out to be I thought I had the Wronskian here. Oh yeah, I do have it. It's 2e to 6x. Just crank it out. 2e to 6x will never vanish, right? It's always non-zero, so therefore they're linearly independent. Okay? Okay. Let me just see. Okay. So again, I'm not going to do this. This is just boring. You should again verify that yourself that all 3 solutions, e to the x, e to 2x, e to 3x, solve that homogeneous equation. Great. So now I have a fundamental solution set, basically, right? I got 3 functions. The set is linearly independent, and each one individually is a solution to the homogeneous equation. So I know from that theorem that the most general solution is given by c1 e to the x plus c sub 2 e to the 2x plus c sub 3 e to the 3x, right? Any solution that someone writes down, if it's a solution to that equation, will always be a linear combination of e to the x, e to 2x, and e to 3x. Okay? And again, how do you get to c's? Well, maybe in order to get to c's, you'd have to have an initial value problem with the value of y and its first 2 derivatives are given at a point. Okay? The thing which I want to emphasize at this point is that when you solve the homogeneous equation, you've got to come up with a fundamental solution set. How many? Matches the order. That's why we have 3 over here. Okay, I guess we have some time left over here. I want to talk about non-homogeneous equations, okay? Let's go back now to L on y equals g of x, okay? We pretty much covered the story on L on y equals 0, but the most important part is how do you get those fundamental solutions I haven't done yet. That's to come. But at least from a theoretical point of view, there's nothing really more to say in this course about that, okay? You got the homogeneous equation, just come up with the right number of independent solutions, and you're finished for that part. Okay, what about non-homogeneous equation now? L on y equals g of x. Remember how I said the solution of homogeneous is a stepping stone to that? And I'm going to show you that right now. Okay. But before we do that, we need another piece of vocabulary over here. It's called a particular solution. Okay. So now we're going to basically go over to non-homogeneous linear ordinary differential equations, okay? In our shorthand notation, that's L operating on y equals g of x. And again, always remember what L on y is. You can keep doing this, for a while until it becomes second nature. Okay, so I got something nth derivative, something minus first derivative. On the right-hand side, I got some function of x, maybe sine x, x squared, e the x is some function of x. And that's called non-homogeneous. And in vibration problems, okay, this would be called a forced vibration response. Because usually what happens is that your free vibration is governed by an equation where the right-hand side is 0. Because physically, this thing on the right-hand side is the forcing function. Once I have this vibratory system and I put external forces on it, it becomes non-homogeneous. Okay? So if you were to read a book in vibration, they probably wouldn't use the vocabulary homogeneous, non-homogeneous. They would call it unforced response, forced response. Okay? But it's really the same thing. Okay? Again, this is on some interval AB. Okay, nth order. And now we need a definition of what's called a particular solution. Any function, and just about all differential equations book use the symbol y sub p of x as a mnemonic for a particular solution. Okay? Any function yp of x such that L operating on yp of x equals g of x is called a particular solution. It's called a particular solution, right? So any function yp of x such that it solves the non-homogeneous equation for the particular solution. Notice that I use the, my English is what's called a veradjective or adverb. I used a, I didn't say the particular solution, because it's not unique. Okay? Two people can look at the same differential equation and come up with two completely different particular solutions. Okay? We're going to find out that they're connected actually. There's a connection between them. That's the key of solving it. Okay? But the important thing is that if you have a function that you claim is a particular solution, it just has to be a solution of the non-homogeneous. Not the most general, just a solution of that. That's called a particular solution. Okay? Okay, and I'm going to end with this theorem, okay? It's not going to take too long, but I want to, get that, and then I guess we'll call it quits for today because we did a lot of fundamental stuff that you should really review until it really sinks in. Okay? Okay, I'm going to write this down, and it's very useful because it actually tells you how to solve a non-homogeneous equation. Okay? So here's the problem that we have now. We now have this non-homogeneous equation over here. Okay? Again, suppose someone gives us a particular solution. Many times, actually, you'll see that the physics of the problem, you can actually get a particular solution without doing any work. Because you know something about the physics of how the thing works, and you can say, oh, I know that this thing will always be at least one solution to the inhomogeneous equation. So the question is the following. If I have a particular solution, and I also have the most general solution to the homogeneous equation, L on y equals 0, is there some way of piecing those two things together to get the most general solution of the inhomogeneous equation? And it is. Okay? It's very, and the end result would be very, very simple. Let me just state it first, okay, and then we'll prove it, okay? And this may be a little bit wordy, but I think it's better to have it this way so you don't have any ambiguity, okay? But remember, the idea of this theorem, or what's going to tell you, is if you're given a non-homogeneous equation like that, how do you actually solve it in terms of a particular solution and a fundamental solution set? Okay. So here it is, basically. I'll try to write this neatly. Let y sub p of x be any particular solution to L operating on y equals g of x. Yeah, remember that? That's that red equation, right? So yp of x happens to be any particular solution. And again, two people can have two different particular solutions. And this set of functions, right, y1 of x, y2 of x, I'm trying to use the same notation I used earlier, y sub n of x, is a fundamental solution set. To L on y equals 0. Remember what the fundamental solution set is, okay? The fundamental solution set is a set of functions, each of which satisfies the homogeneous equation, and they're linearly independent. Okay? Of course, like I said, the big job is how do you get to set y1, y2, yn? How do you get yp? Okay? But let's just see at this point, if you had them, what would you do with them to get the most general solution? So I start off with yp of x, that's any particular solution. Okay, I know a particular solution, right? I just plug it in and make sure it satisfies the inhomogeneous equation. Okay? And then also I'm so lucky enough to get this fundamental solution set, right? Each of these guys satisfies the homogeneous equation and they're independent. Okay? Then, this is another paragraph, right? Then, the most general solution to the inhomogeneous equation, right, is given by, what is it? Y of x is equal to the homogeneous solution C1 Y1 of x plus C2 Y2 of x, right? You've seen this before. This is the old superposition of homogeneous solutions, right? Plus C sub n yn of x plus the particular solution y sub p of x. Okay? Okay? And we'll discuss this a little proof and then we'll put it to that. Okay. So, again, we'll start from the beginning over here. We've got this inhomogeneous equation, L operating on y equals g of x. Okay, so I know all the coefficients, I know g of x. Okay? And then I'm going to basically construct the most general solution to the inhomogeneous equation based upon two components. The first is what's called the particular solution, right? We know what that is. Yp of x is any particular solution. It means basically that you do L on yp, you get g of x. Okay? But that's going to be that's not the most general solution to the inhomogeneous equation. There are others. Okay? We want to make sure we don't lose any. Okay? But the great thing about this theorem says you have to start with some particular solution. I don't care what it is. Let yp be any particular solution. But you must have the fundamental solution set. That's what these guys are. Remember? Little y, little y2, yn. All of them satisfy the homogeneous equation and they're independent. Okay. So I got two things now. I've got the fundamental solution set and the particular. What this theorem says is that the most general solution to the inhomogeneous equation is given by this box thing. What does it say? Well, first I got a linear combination of the homogeneous. We saw that before when we were solving the homogeneous. And all you have to do is add on any particular solution. So that's amazing, okay? You don't have to do anything more complicated than expand this guy. So long as you would attach to the particular solution the most general solution to the homogeneous, you've got every solution possible in there, okay? And again, what's going to happen is that imagine you have an equation and two people solve it, they come up with a different y particular. So one guy says, oh, I'm going to use my y particular plus this, you're going to use your y particular in this. Comes out that the difference of those is absorbed over here, okay? Let me just show you the proof of this thing over here. See, it's even simpler than the one from before. Okay, and again, how do you prove? Let's look at the conclusion over here. It says the most general solution to the equation. So again, think about it. It's a challenge. Someone gives you a function we'll call big Y of x, okay? And that big Y of x could be anything, but it solves the inhomogeneous equation, okay? I want to show you that his big Y of x is always written in the form of a linear combination of the fundamental solution set plus a particular. Okay, so here's the proof. Consider any solution to the inhomogeneous equation. Okay, I have to say any because I claim that any solution is given by that, right? Consider any solution to the non-homogeneous equation. Let me actually give it a label here. Consider any solution, we'll call it big Y of x. Okay? So that's the one, you know, your friend gives you, give him the differential equation, he says, I've come up with a solution to L on Y equals G. Okay. So consider any solution Y of x of the non-homogeneous equation L operating on Y equals G of x. Okay. So, what do we have here? You've got this, your friend gave you a solution, big Y of x. He claims it's a solution to the inhomogeneous equation. You can verify that. So, we'll give him the benefit of the doubt. L operating on Y of x is G of x. And we can check it, right? Yeah, his Y of x is a solution to the inhomogeneous equation. But we also have a solution to the inhomogeneous equation, our particular one. That's our favorite one, right? So we have L operating on Y particular of x is equal to G of x. Now, does that mean that little log Y particular and his big Y are the same? No, it's not the same, right? Remember I said it could be completely different, okay? But we do know that his big Y of x is a solution to the inhomogeneous equation, and our Y sub p of x, again, is a solution to the inhomogeneous equation. What we do now is take these two equations and subtract them. L operating on big Y of x minus L operating on Y particular of x is what? Is equal to 0. Can't argue with that. L is a linear operator, right? So the left-hand side could be written as L operating on big Y of x minus little y particular of x is equal to 0. Whoa, that's the homogeneous equation, right? I know the most general solution to the homogeneous equation, right? It's the sum of the fundamental solution sets. We proved that a few minutes ago, right? You have homogeneous equation, L on junk equals 0. That junk is just